This is the CPSS project sponsored by Otter Tail Power Company, and our project title is Communication Assisted Powerline Tripping. And my name is Jeremy Nelson, and my team members are Ryan Kleinjohn and Reese Chambers. Our advisor is Dr. Hebus. So who is Otter Tail Power Company? They are headquartered in Fergus Falls, Minnesota, and they consist of a generation, transmission, and distribution set. They own approximately 800 megawatts of generation, which is from 3 coal plants and 4 wind farms. They operate over 5,000 miles of transmission line and serve 130,000 customers. And all this can be found on their website. Our project consists of 100 miles of 115 kV line. We'll be dealing with 3 substations and 1 generator, and we'll have to use the SCADA communication link for most of our project. So here's a picture of what we're dealing with. We have substation 1, which consists of their generator, an SCL 421 relay and SCL 311C relay. Substation 2 has a 421 relay and a 311C relay, just like substation 1. Substation 3 has a 321 relay, and as you can see, it's a 3-terminal line with all the SCADA lines running that go back to Fergus.
So the problem we're facing is that Otter Tail's protection scheme has slow tripping. They currently use a step distance protection scheme, which does not use a pilot method. Typically this tripping happens within 5 to 25 cycles, and the problem with this is if the tripping is too slow, then faults cause instability in the system, which cause relays and other parts of the system to trip. A little summary on what step distance is like I said, it's non-pilot. There can be up to 4 zones. The first zone covers about 80 to 90% of the protected line. This has no delay in the tripping. Zone 2 is 125% of the protected line. This has a slight delay in the tripping. Zone 3 is 50% in the reverse direction, which has an additional delay to it. And then zone 4 is 200% of the protected line, and this also has an added delay. So for example, looking at this figure, if a fault occurs at the red X, then there will be a delay in the trip, which causes the instability, which is what we are trying to fix. This list just shows a summary of the different protection schemes. There was a site found that showed of over 900 different schemes, so this is just some of the more common ones. The schemes on top there that have the acronyms beside them, those are different distance protection schemes. Those they calculate the impedance and can tell you where exactly the fault occurs. Overall, these schemes use a mix of pilot and non-pilot methods, so we will be doing some more research into the ones with just the acronyms on top there.
Some of the current pilot or communication mediums that transmission lines use are power line carrier. Pros of that are that it's fast, cheap, and secure. Con is that it could be unreliable depending on how the system is configured. Another medium is optical fiber. This is fast, reliable, and secure. Cons are that it's expensive. Microwave or radio communication. Pro is that it is reliable. The con is that it's slower. Dedicated telephone line. A pro is that it's secure. A con is that it's expensive. And Otter Tail communication uses a combination of optical fiber and digital microwave. Part of the motivation for proposing this project has to do a lot with system stability. Faults on a line need to open a breaker, and if the nearest breaker is not opened as fast as possible, another breaker further down the line could open, which could cause more power outages than what is needed. A breaker near a generator needs to trip as fast as possible so current isn't flowing through the generator and causing damage. Further motivation is that, as we mentioned before, it could take 25 cycles to trip a breaker, and that could cause damage to transmission lines or generators, or even be harmful to people that are nearby. The deliverables for this project are that we will be testing different protection schemes that Ryan mentioned, and the one with the fastest trip time will be suggested for Otter Tail to use with their current system. We will also be using Otter Tail's Ethernet by means of converting the Ethernet ports on the SEL relays or the use of signal multiplexing.
These are a list of the specifications we plan to meet. We shall trip all 3 associated breakers in less than 417 milliseconds, or 25 cycles. Software model trip time for the 3 associated breakers shall be within plus or minus 10% of the existing system. The software model communication delay shall be within plus or minus 10% of the existing system. For the hardware model, we shall have a breaker trip time within plus or minus 10% of the designed software model. For the protection scheme requirements, the protection scheme shall detect faults and trip associated breakers in under 333 milliseconds, or 20 cycles. Also, the protection scheme shall detect 100% of line to ground faults on transmission line in question.
Here are the constraints that we are limited to. Otter Tail currently has a digital microwave, fiber optic, and Ethernet communication setup. We plan to use this because constructing another communication system will be costly. Aspen software will be used to model the communication and the protection schemes. The communication side will be difficult because of the constant change in latency based on the channel traffic. The constraints in the hardware, we obviously can't model this system in real life, so we'll use a scaled down version. Some of the ratios listed for power is 10,000 to 1, the voltage is 480 to 1, and the current is 20 to 1. These ratios are subject to change based on what can be used in the lab. Also, the relays that we'll be using are 311Cs, 321s, and 421s, which are provided from the school and from Otter Tail. And then latency methods will need to be employed either by hardware or software methods.